Hello, welcome. Thanks very much for attending. My name is John Bruner. I'm one of several with DSM supporting customers with design and CAE. That's computer-aided engineering related support. And I would like to show some of this with you now. If you have questions along the way, please feel free to use the chat option or chat application. Thank you. All right, so what I'd like to show in the next 30 minutes or so is the following. I'd like to cover these topics first with a very brief overview of the DSM portfolio. Next, we'll see the role of CAE supporting customers' product developments, then how and why we develop methods, and our portfolio of CAE expertise. Finally, the bulk of what I like to present will be on one of several DSM demo cases, specifically on a DSM in-house mock-up of a molded EPS, that's a electronic power steering housing part. If you were to look at DSM's position, we basically play on the right side of the pyramid in the realm of CAE crystalline materials, shown here. This includes a broad offering of our Aculon PA6 and 6.6, Finite PBT and PET, applicable in high precision components for the automotive and electronic industry. There's also EcoPax, a PA410, a high performance bio-based polyamide providing low moisture uptake and excellent molded surface finishes. Working up the pyramid, we have Stenil 4.6 for excellent high temperature mechanical properties, and this also provides good, excellent wear and friction behavior, and it also flows nicely. Last but not least, our newest, the 4T platform. At the top here includes polymers that are the highest crystalline, highest melting point, and highest glass transition temperature amongst all PPAs in the market. So with this broad, high quality materials portfolio and in-depth technology know-how, we work in close collaboration with customers across the globe to develop new applications. And you'll find our products in a wide range of applications. As a global supplier of high performance plastics, DSM has built a global leadership positions in a wide variety of industries by designing and developing better, smarter, stronger, safer, smaller, lighter, longer lasting, or more sustainable solutions. Our dedicated teams of industry experts, scientists, and engineers can and do work closely together with our customers and find ways to realize successes across the globe. So CAE enables this modeling of these new components, reducing the risk in designing and manufacturing parts made from thermoplastics. This then increases confidence in your design, ensuring no compromises when it comes to safety, quality, cost, and time to market. Additionally, we just cannot keep up with the rapidly accelerating pace of the market without simulation and virtual prototyping tools. Okay, so if you look at who we are, the people that are doing the simulations within DSM, here's our team. As you can see, we're positioned globally, including locations in the US, the Netherlands, Japan, China, Taiwan, and India. Right, computer-aided engineering and product development. So when do we utilize these tools? Well, I suggest first the earlier the better, but also throughout the development cycle for different questions that may arise. We understand that making physical prototypes for strength and stiffness testing is a heavy burden, both financially and time-wise, for manufacturers, since they would need to make and test a variety of designs. Using CAE eliminates the need to prepare physical prototypes, or at least reduce this, i.e. changes to the part shape to evaluate the relative merits of different designs under various conditions. And then this helps manufacturers to reduce the time and cost spent on design testing. Finally, as the automotive industry moves towards mass adoption of environmentally friendly electric vehicles, we are seeing a move to replace a wide variety of metal parts with engineering plastic materials. We expect this trend to accelerate as we move closer and closer to fully electronic and self-driving vehicles. As our customers consider metal to plastic conversion for their components, we, DSM, remain at the ready to support you through the process with low cost and efficient design verification service using CAE. What do we need to support this? We need a global CAE team to support global customers. We need the necessary software tools and know-how. We must also proactively and aggressively, so I would say, develop material data needed for simulations. We must also establish and develop connections to our customers and others, and also develop continuously and continuously improve our methods. And by the way, speaking of data, we do have a location that you can go to download a variety of information and material data to support your needs. This is called Plastics Finder at the address below here. So why do we develop methods? Well, one, to improve accuracy for making our designs more efficient and for lowering the safety factors. And also for creating a better understanding and to stay an expert, to be ready. And this is needed to be for us to be able to quickly support customers with more difficult projects and operate at a high level with, I would say, the same level of understanding as academia and our software developers. How do we develop the methods? Well, in cooperation with software suppliers, academia, and customers, and also internally with our team of DSM scientists, in case the aim is to get a better understanding of our own materials. If you look at our expertise areas, we have these broken out with conceptual design, and that includes the functional integration, how we attach plastics to metal, for example, also metal to plastic conversions. And then we have a whole host of expertise within the structural realm, including static stiffness and strength, dynamics, fatigue, creep, NVH, including natural modal frequencies, force frequency, vibrations, gear design, and also on the manufacturing side, including injection molding simulation, blow molding simulation, and other areas, including thermal type problems and EMI. How can we support you? With our team, we can support you with conceptual design, again, and metal plastic conversions. We can be a partner. We can be a kind of a discussion partner for your CAE department, which helps boost the confidence in DSM products and helps DSM actually better help you. Also sharing advanced modeling know-how, and also delivering reliable material data sets for the simulation. CAE data is not so ordinary and readily available. Having these connections are therefore important. And all of this equates to helping you getting the maximum performance out of the DSM materials. Okay, next I'd like to walk through our showcase, our metal replacement of our demo EPS housing application. This includes, what was involved with design engineering, as well as analysis, both structural and flow analysis work, and what we do to advise customers on injection molding, tool design, process optimization. So this is both, in a way, a capabilities presentation, but also an overview of how we approach doing demonstrations of parts. So there, with the EPS housing, there was an existing metal housing. These were typically aluminum. They're cast machined. And the drivers for replacements were the cleaner production, the advantages in production, no machining, and generally increased mold life with injection molds versus cast molds, and weight reduction to reduce cost. If you look at some of the challenges for these housings for electronic power steering, operating temperatures range from the -40 to the 125°C. You have some aggressive loading requirements for the bolt tension and the rack and the torque. There's also a variety of chemical resistance requirements typical for automotive. Dimensional requirements were very tight. You need to have a very accurate dimensions on your holes and mounting locations. And the fixation of the other parts, the assembly requirements, is also a challenge. So if we look at what is needed from an analysis standpoint, it's got to fulfill the need. It's got to be functional. You got to consider all the boundary conditions and requirements, understanding of the design space, and also cost. What is your objective cost-wise? This will drive other decisions with your mass, your allowable mass. Also, you need to have some creativity. You need to have some ideas of how to conceptualize a design for functionality. And this all feeds into a concrete design proposal that meets the needs of environment, the requirements of the load cases, moldability, manufacturability, the aesthetics, and iterations might be required, but this leads to reduced prototypes or even potentially elimination of prototypes. And design optimization. Let's see. So for structural analysis, we approach this with the finite element method, or finite element analysis. We're evaluating mechanical loads, the force displacements. We're learning or attempting to gain an understanding of the fiber orientation, capture the fiber orientations needed for the structural analysis. Understand the flexibility, or the complexity rather, of the failure mechanisms. And in this process, we're evaluating different designs, and we're comparing our designs or simulations with the actual performance of the part, of the molded part. A little background. These are injection molded parts. If you've never seen one, this is what an injection molding machine looks like. You have it's a very basic description of a machine. You have the injection side, where the polymer and the granulate is entered into the hopper and feeds through a screw and barrel and processes the melt, injects the melt into the mold under high pressure, and remained closed during that process on the clamp side of the press. Let's see, so what are the main mold functions? Here we have shaping, cooling, releasing of the part. All three functions mentioned above are equally important. Often cooling and release functions are underestimated, however. This means that in the construction of the mold, all three aspects deserve the same attention, which is certainly not the case generally speaking. In today's reality, the mold maker is first of all interested in the shape of the and dimensions of the cavity. Next, he will place his ejection system. At last, he looks at the cooling and puts in the cooling lines in the space that is left. This way of constructing a mold can and often leads to less optimal of a mold design. The thinking here is the cooling system should get more or special attention, especially for the higher end technical parts. This is what this particular mold looks like for the Eps housing. And on the left, you got the full assembly. You got the A side. This is the side where the melt enters, and the B half, or the moving half of the mold, is where the core side of the mold. If exposed, this is what it looks like. You have kind of a reverse of the inside of the Eps housing. So this is a CAD illustration of this mold. So here we have both the image of the mold, the actual mold that was cut. Below is the illustration, the CAD illustration of how this is done with conformal cooling. We have some very thin steel that needs to be cooled and is not able to be cut with traditional means or traditional type of gun drill holes for cooling. The above printed portion of the steel core incorporating the conformal cooling of the cooling circuit is an additive process. The process starts with the placement of the completed CNC core, which is shown here, into the additive manufacturing or the 3D printer for creating the printed portion. And then the two are essentially fused together during that process. So here's a better illustration of the core with the cooling circuits, the blue color representing the actual cooling circuit, and the pinkish orange or beige color representing the steel. On the left, you have, again, the CNC portion of that core block. Here you have the additive manufacturing or the printed portion of this. And again, this printed portion is the key. It's the magic. It's what allows for the non-conformal type of cooling channels, these nonlinear channels, to be formed. And here's sort of a close-up of this. So this is something, again, you wouldn't been able to do otherwise. It has to be printed, and we're able to get sufficient cooling through these thin cores, making nice dimensionally correct parts. So this is the bulk of the non-conformal cooling circuit, which begins at this intersection, I believe. Everything else is done with traditional channels. And then these loops that are above here, shown above this surface, are also the non-conformal part of the circuit. Below it, it intersects with the traditional machine gun drilled circuits. So, okay, enough on that. And then, all right, so here's what the mold looked like during the assembly, or showing, the side cores that form the sides of the part. It's a fairly complex mold. There's a lot that goes into one of these molds. albeit a demo or demonstration type of mold. There's quite a bit of effort involved with this. All right, so when we assist customers when advising on tooling, advice might include how to position the part in the tool, where the parting line should be, how to gate the part, where the melt entrance position should be located, layout of cooling systems, layout of ejection systems, and also specific types of steel that work best with our particular materials. And lastly, molding simulation is also intensively utilized, including MoldFlow and MoldX 3D within DSM. So what does a mold filling simulation look like? This broken out into several phases. The mold filling portion, which could include the packing phase as well. On the left is the filling animation, blue representing the beginning of the fill, and red is the end of fill locations. So this part of the analysis, we can learn lots of things here. It could be used for the gating, optimizing the tool, the runner systems. And it also could be good feedback to your designer to improve the design to make it more manufacturable. You would, at this part of the analysis, look at your injection pressures, make sure that it's reasonable. Is it manufacturable? And is it going to require a clamp tonnage that's reasonable? Is it going to work with the machine that you have targeted? The next part of simulation might include the cooling channels. This is where it gets real, or can get very complex. As you can see, there's a lot of modeling, a lot of consideration. This is for this Eps housing. All of this was included. The traditional cooling lines as well as the non-conformal circuits. And then the final part of the simulation is the predictions of part deformations, the warpage of the part. Okay, so with an integrative simulation approach, the effective processing is and can be included in determining the application performance. Basically, what happens, the orientations of the glass fibers, or could be carbon fibers or fibers of any type, is determined during the injection molding phase, which then determines the local mechanical, or ultimately the local mechanical properties, stiffness and strength. So as designers and engineers replace metal parts with parts made from lightweight thermoplastics, being able to accurately model the part's performance is critical. The properties of injection molded short glass fiber reinforced plastics can vary depending on temperature, strain rate, and the orientation of the fibers. Computer-aided engineering tools enables this modeling of these new components. So to reduce the risk of designing and manufacturing parts made from thermoplastics, increasing confidence in the new design and ensuring no compromises when it comes to safety, quality, costs, and time to market. All right, so fiber orientation. This is an output, a result of fiber orientation from the flow analysis software. Either this could be, again, MoldFlow or MoldX 3D, and there's certainly others capable of this. And this is what it looks like. If we zoom in, you can then see what the orientations are represented in ellipsoids. So very thin or skinny Ellipsoids represent more higher degree of orientation. The more rounded ellipsoids are much less orientation. Then it also provides you kind of a vector with, a direction of where the fibers are going or being oriented. So if we zoom in further, where there's a higher degree of orientation, we can then capture the properties using tools like Digimat to determine the the flow direction as well as the cross flow direction, first principle and second principle directions. In comparison, there's an area or an ellipsoid with much less orientation. This is what the two stress strain curves might look like. They're fairly close to one another. So here's kind of a workflow of how we use these tools like Digimat to include these properties in our structural analysis. I'd say while there has traditionally been a lot of data and documentation available for metals, it has been more challenging to replicate the behavior of complex materials until now. Simulations can now integrate the effects of molding processes on material properties to create complex structural finite element analysis, FEA models. So here on the left, we begin with experimental data measurements utilizing a large plaque, and we basically cut these specimens out of the plaque and different degrees of orientation, in the flow direction as well as the cross flow, and then there will be typically one that's at 45 degrees. And this dot here represents the gate location. So these measurements are then fed into our Digimat software to create these Digimat type of models that ultimately feed into our FEA simulation. There's also some other characterization, some microstructural characterization, including fiber orientation, the aspect ratio, the volume fraction, that's used as a verification of the Digimat model. And let's see, so far we've applied this in 3 of our demo modes, the Eps Housing. There's some beams that are also completed and another bracket. So when we develop the data, we also work with our vendor Digimat, Extreme Digimat, to provide them our data to be input into their database. This is called the MX database. And typically for short glass fiber reinforced compounds is what you see here. Currently, we have over 100 input decks available and ready to run. I should emphasize fiber orientation prediction is also essential for correct warpage predictions. It's not just for structural considerations. Okay, so since DSM approaches all of our material sales as a partnership, we have measured the stress strain behavior of our materials to derive thorough input decks for the Digimat software. This enables us to work even more closely with our customers and to identify future needs for material models, such as the effects of temperature, humidity, and crash behavior. Our teams check the accuracy and robustness of our material models by using in-house testing on injection molded parts to validate that our material models provide accurate predictions. Through this rigorous testing, we have successfully verified excellent results for stiffness, eigenfrequencies, and load of failure. We've also developed new models to get good results for the fatigue performance of our materials. So here's a quick look at the black, a little bit better illustration of this. Again, you have the 0, the 90, the 45 degree. This is on a fairly large size black. This is our standard black that we use currently. And the flow direction, it's moving in the vertical direction here. And I think it's good to know that all the specimens are cut from the same center point in the black. And from those measurements, you can see the results here. This particular one is of our PET material. It's 50% glass at the 23°C room temperature, and these curves are averaged. The plaque measurements are these bottom 3 curves here, the blue representing the 0 degree or the flow direction. The cross flow direction being represented by this yellowish curve, and the 45 in the middle, actually fairly close to the 90 degree curve. So I think it's important to note the difference between the flow and the cross flow direction. And we also have the curve for the ISO specimen, which is a molded specimen where you typically or should get higher degrees of orientation. So it's important to note what you might see on a standard data sheet from a molded ISO specimen will differ a bit with the plaque specimens. So here's some molded parts of the EPS housing, and these were tested again at the 23°C, and we're showing the fractures that were produced. You can see upper left-hand corner, there's a kind of a crack that progression through the side here, and we flip that over, there's another crack here. Look on the inside, you have a couple of fractures here and here, and another one here. And let's see, if you compare that with the simulation utilizing the integrative approach, you can see there's a fair amount of agreement with the prediction. You got you compare this location with here, and these with this location looks fairly comparable. So here's some additional results with the EPS housing. This was at the 105°C test temperature for this particular load case. The blue curves, 15, 16, 17, represent the experiment or the actual test, and the red and orange curves represent the predictions. And as you can see, there's a fair amount of agreement, providing just excellent prediction of the force at failure. We zoom in on the top part of the curve. That's what that looks like. All right, so here's an overview of the results. Some additional results. We are comparing the predicted force at failure with the measured force at failure in newtons, and as you can see here, there's a fair amount of a good agreement between the two. What we have here represented in the blue dots are a PET with 50% glass and the PPS with 40% glass represented with the red dots. And these are basically 9 different cases, including 4 to 5 temperatures. And they all fall within this basically this window of meeting our goal for 10% accuracy. So that's good. Here's a complete overview of what was involved with this and what we can provide customers. This began with the design, the flow simulations, and the full simulations, including the filling, the packing, the cooling systems, and warpage. And then from the flow analysis, then you obtain the fiber orientations. This feeds again the mechanical simulations. If all goes well, then you're off to tooling construction, producing, molding a part, testing the part for all the different load cases, and comparing the results. In this particular case, all looked fairly comparable between simulation and test. I want to cover some ideas on how to get data from DSM. First and foremost, you can go to Plastics Finder. There you can find the standard material property data sheets, injection molding recommendations, etc. There's quite a bit of information there. Stress strain data can be obtained. Again, if you need something more elaborate, then you may need to obtain that through the other software, including Digimat, or contacting DSM directly. As for mold flow data and MoldX3 data, they also have database, and we have, I think, something like over 250 grades fully characterized for those simulations as well. So, and if it's something new, relatively new, then you can again contact DSM. All right. I'd like to acknowledge a few folks, my DSM colleagues, Lucian Dovin, Andy Rose, and Hare Rutin, all contributed considerably to these demonstration molds and helped provide some of the presentation material for today. So, okay, so that concludes my presentation. I want to thank you. Thank you for your attendance. If you have any questions, please, again, use the tool, the chat tool, and I'll get back to you with via email. Thank you very much.